at this time. That's okay. The idea here is to have a seminar on natural language processing primarily from a Swedish perspective. So things that are relevant for us in Sweden or things that are being done here in Sweden in natural language processing. And it works in the following way. So we have a presentation for 45 to 60 minutes, something like that. And then we have lots of time for questions, comments, and discussion. We record the presentations, but we stop the recording during the discussion. Also, if you have comments during the presentation, please write them in the chat. I will keep an eye open for the chat. And then during the discussion, you can either use the chat or raise your hand. And I will keep a list open for those who have raised their hands. And I will then give you the word. So please turn on your camera and microphone and post the questions in person. We really encourage active participation. I think that's it. Is there anything I missed, Johanna? No. So with that, then I will welcome our speaker for this first seminar of the fall, which is Styliani Katsarou from Peltarion. So please, Stella, go ahead.
Yes, thank you, Magnus. Thank you for having me here. And I was very happy to see that the webinars, the seminars will be happening in real life as well. It's very nice to feel that we're going back to normal gradually. So I am Styliani Katsarou. I work in Peltarion. Today in Peltarion's AI research team. And today I'm going to be presenting the work that I have done for my thesis work. So let me share my screen. All right. So the title of the thesis project is Improving Multilingual Models for the Swedish Language, Exploring Cross-Lingual Transferability and Stereotypical Biases. Has been supervised by Anders Arptek at the time he was working in Peltarion and Borja Rodriguez Calves from KTH. So yes, this is what it is. It's a thesis project. We're going to be talking about this project today. And this is a global overview of the structure of this project, which is also the structure of the presentation that we're going to be having today. So this consists of two parts. First one being improving multilingual models for the Swedish language. And the second one has to do with stereotypical biases of those models. Every part consists of a background section and an experiment section. So as you can see, it's the same here for stereotypical biases as well for the second part. But you will be able to see those parts on the side of the slides at all times so that you can have a sense of where we are with respect to the progress of this presentation. So here we are at part one, improving multilingual models for the Swedish language, and we're going to be covering some background with respect to that. So what is the motivation behind this work? So usually what we mean when we say transfer learning in NLP is that we start from a pre-trained unsupervised model, and then we just fine-tune it in a supervised way. To do that, thankfully, we have most of the times models that are released by the authors, and they have been open sourced. We have their checkpoints, and all we have to do is use our labeled datasets in order to fine-tune them. A problem that exists is English centricity, or in general, high resource languages centricity, which means that most of those models here are available in English predominantly, but in high resource languages as well, and here as well. So here, when it comes to labeled datasets, we have a lot of them in English, but we strive to find datasets when it comes to low resource languages like the Swedish language, for example. A solution that the community has provided is multilingual models. This is one of the solutions. Another solution, for example, can be that we have monolingual models. But here we focus on this, on multilingual models. Another problem that arises from this solution is that we can see it has been proven that the performance of multilingual models might be worse from the performance of monolingual models that have a similar size of the multilingual counterpart. So this is the motivation behind this project. We were thinking, why don't we focus on a multilingual model and try to make it better for a low resource language? So this is what we tried to do. And those are our research questions. So first, we focus on the multilingual model MT5, and we say, can we actually improve this by further pre-training it? Can we improve it for Swedish? If we manage to do that, then does this affect the model's generalization capability? And then there is a third question that has to do with stereotypical biases, but that one we're going to visit on the second part of this presentation. So I mentioned MT5, so I thought it would be nice to talk a bit about T5 and what it does and how it works. So after the BERT paper was published, people were excited and they tried using different architectures, different pre-training objectives. They were tweaking a lot of parameters in the models and how they can train them in order to obtain better performance. So it can be hard to actually keep track of the contribution, of the relative contribution of all those changes. So the authors of this model, of this paper, said, we've had enough. We're going to create like a unified framework for us to do like a huge ablation study of all the pre-training objectives, of all the pre-training data sets, architectures, whatever it is out there. But in order to do that, we need a unified framework, like a clean experimental environment to do our experiments on. So they came up with T5. So T5 is more of a software engineer necessity in order for us to do our experiments more efficiently. So what it does, it is a model that can handle multiple tasks, and what goes in is text, what goes out is also text. So it speaks human language, essentially. So for example, if I wanted the model to conduct the downstream task of translation, all I had to say was translate English to German, and then the input sentence, of course, and that is a string. Then I would have that inputted into T5, and then I would get the translation in German. And if you can think of any task that can be casted in a text-to-text format in such a way, then T5 can handle it. For example, if you want to check whether this sentence is grammatically correct, you would say call a sentence, colon, the sentence, and then T5 would say not acceptable as a string in human language. So that is what text-to-text framework is. The pre-training objective of this model is inspired by BERT, but it is a variant of it. So let's have a look at it here. Say that we have a piece of text. This is the original text. What we do is that we corrupt some of the words. They corrupted 15% of the words independently, uniformly at random. And then if it happens that the words are in consecutive order, then we just replace them with one unique sentinel. That's how they call them. And that is the input to the model. The target, instead of the whole original text, is only the parts that are missing. So in this case, we would have the sentinel token X accompanied by the text that has been missing in the input. So that's the input and that's the target for this model. And that we do, and we pre-train our model on a huge data set of clean English text, which they call C4, and it is approximately 750 gigabytes. So here is a visual example. It's yet another example. So it's a question answering example. Here we have the question, our paragraph, and the target. Of course, the answer to the question can be found in the paragraph, and it is our target. How does BERT and T5 handle this task? Well, in BERT, you have to formulate the input in a specific way, put your CLS token, your separator. But in T5, all you have to say is question, colon, then the question, context, and then you have to put the paragraph here. That is this text. Then you also have to do an additional step in BERT. You have to use a classifier, and what you get is a start and end span, which you have to map on the paragraph in order to find where the answer actually is. But T5 yields the answer for you. You don't have to do anything. And it is a string, it's human language as well. The bad thing about it was, of course, that it was in English only. So in late 2020, MT5 was released. It needs fine-tuning because this one has not pre-trained. So what they did in pre-training was, they call it multitask pre-training. So they pre-trained both in an unsupervised way, but also on a number of downstream tasks. But for obvious reasons, we cannot do that with MT5 because we have 101 languages, most of them being low resource. So it needs to be fine-tuned. The corpus that they pre-trained the model on is called MC4. It is a huge data set of 27 terabytes covering 101 languages. In there, you can find 6% of English and approximately 1.6% of Swedish, which corresponds to 45 billion tokens. This is a very interesting matrix because, I mean, I find interesting the comparison between the monolingual and the multilingual variant of T5. Because as you can see here, if the models are similarly sized, for example, small, then the multilingual model is going to be worse than the monolingual one. There is a threshold here, though, after which the performances are almost similar. This is the squad task, by the way. So yes, we would like to focus on the smaller versions of the models instead and try to improve them and make them potentially as good as a monolingual model would be. So this is, again, the motivation behind this study. Here we can see the architecture. This is an encoder-decoder model. This can be a big model. And I say can be because there are many variants of it. The smallest one is 300 million parameters. Then we have base, which is approximately 600 million parameters. Large, which is 1.5 billion, and it can reach up to 30 billion parameters. It covers 101 languages, as we said before, and yes, the MC4 dataset that it has been pre-trained on is, they used Common Crawl to create it. So moving on to the experiment section. So we're going to be working a lot with a downstream task that is called Semantic Text Similarity. And here we see how we formulate the input so that it can be digested by the T5 and MT5 model. We use the STSB dataset. It was originally published in English, but then we had this Why Not Simply Translate paper by Salgren and Isbister, who translated it for us in Swedish. So this was the dataset that I use. And yes, so this is how an original example from this dataset looks like in the first row. So we have pairs of sentences. For example, an airplane is taking off, a plane is taking off. And then the target is a floating point, which is supposed to be expressing whether these pair of sentences are similar with respect to context or not. So what we do in order to feed this to T5 and MT5 is we use the prefix again, STSB sentence 1 colon sentence 1, sentence 2 colon sentence 2. But what do we do with the targets? Because this is essentially, because this is essentially like a regression problem, right? So what we do is we use buckets. So every time we would round this number either to the closest 0.1, which corresponds to bucket size 0.1, to the closest 0.2, or to the closest integer. And as a result, because the similarity scores are from 0 to 5, if we round to the closest integer, we would end up having like 6 classes, 0, 1, 2, 3, 4, 5. Here we would end up having 26 classes, and here 51 classes. So we do that in order to make it easier for the T5 model to handle this task, feasible to handle this task. And yes, we test all options and we finalize the third one. We use the third one for the rest of our experiments after some trial and error and seeing what works best. So this is a schematic representation of what we customarily do. We usually start from a pre-trained model, and then we fine-tune that model on a downstream task. Here we start from the pre-trained MT5 as it was originally released by the authors, and then this is the suite of the fine-tuning experiments that we conduct. We either start from Swedish, we fine-tune the model for Swedish, and then we either, of course, test for the same language or we test for the opposite language. And this is why we call them zero-shot cross-lingual experiments. And we also visit the opposite scenario of fine-tuning in English and then evaluating either in English or in Swedish as well. The next thing that we do, and this is how we try to make it work better for Swedish, is that we have an additional layer of pre-training in between. That we call further pre-training here. And what do we further pre-train our model with? So we have two scenarios. Either we use a data set that is smaller, 700 kilobytes, or a data set that is 7 megabytes. In both cases, this data set can either be in pure Swedish or it can be mixed in English and in Swedish, but it is always 700 kilobytes. The same for this one. It can either be 7 megabytes of Swedish or it can be mixed. If you are wondering what those data sets are, so in this case, what we do is we take the STSB data set, we remove the labels, we concatenate the sentences, and this is how we create raw text to further pre-train our model on. And here, to create those data sets, here we use the named entity recognition SUC 3.0. We do the same, we remove the labels, we just concatenate the sentences, and there you have it. And in order to create a similarly sized one of 7 megabytes, we use, again, 3.5 megabytes of the SUC, and then we also use 3 megabytes of MNLI in order to derive, to have a mixed data set. This is not maybe the best case scenario, because if you just take samples and you just concatenate them, then you can't expect your text to have any coherence or any cohesion. But yes, we wanted to see what happens in the case that we have limited data resources. Can we just take the same model that we fine-tune the model on, further pre-train the model on it, and see if we get better results? So this is why we did that, following the simplest approach possible. If we unpack this, we can see that we have this suite of experiments. So we always conduct the same fine-tuning experiments. This is always on STSB, either starting from Swedish and evaluating in both languages, and the same for English. What differentiates those groups is where we start from. We either start from no additional pre-training, or we start from further pre-training, and we do that twice, once for the small data set, one for the bigger one. And then yet again the same for the mixed data set, once for the smaller one, once for the bigger one. So if we go to the first case, which is when we only fine-tune, as you can see here, we have our results. And what do we see here? Every column is the fine-tuning setting. So this is the language that we fine-tune on. This is the language that we test on. So as explained previously, we have 4 combinations, and every row corresponds to a different model size. But yes, let's comment on this a bit. So we see PCC is Pearson correlation coefficient. It's the metric that we report for this specific data set. So we can see that if we test in English, no matter the fine-tuning language, the performance is always going to be better than if we test in Swedish. That you can see in this row and in this row. Yes, this potentially happens because of the knowledge that the model has already acquired during the pre-training process. where we can find like 6% of English, but only 1.6% of Swedish. So this actually is being expressed when we fine-tune the model. Then another conclusion is that fine-tuning in English and applying for Swedish works really well. So this is a very nice scenario. This is what makes multilingual models attractive. We do not have many labeled datasets in low resource languages. What happens if we find a similar dataset in English? Can the model then zero sort for Swedish? And we can see that happening in this table. We can see that here because we fine tune in English and then we zero sort in Swedish. And if we compare this one to this one, where we do have a data set to fine tune on, then you would see that those results are not too much better than those results. They are very, very similar. Then another conclusion is that there is a positive correlation between model size and performance. That one we expected to happen, and you can see that it works for every setting. The bigger the model gets, the better the performance for all 4 settings. Then we go to the further pre-train fine-tune scenario. And here you can see the results for the smaller data set, the bigger data set. Every column corresponds to a different fine-tuning setting. And every row corresponds to either the baseline, further pre-train in pure Swedish, or further pre-train on mix. Some conclusions that we can have from this one is that if we further pre-train in Swedish or in mix, then we improve the model for English. If we further pre-trained in Swedish or mix, we can improve the model for Swedish, given that we have a Swedish dataset, annotated dataset to fine-tune it on, that you can see here. So here is the no further pre-training, and then we would need to have like, yes, we do need to further pre-train in Swedish raw text, but we also need to have an annotated dataset to further improve it, and then it improves for by 4% approximately. It also improves for English, as we said, which is really nice. And then we can see that further pre-training has no negative impact on the model's generalization capabilities, because I mean, the point is that you have a model that works really well for English already. So then you further pre-train it in Swedish. So what will happen? Will this compromise the performance for English or not? And we see that in all cases, it improves the performance for English, or the performance stays the same. So no, it does not negatively affect the generalization capabilities of this model. This is a reminder of our research questions. So the first one is whether we can further pre-train and improve the model for Swedish. The answer is that yes, we can do that under specific cross-lingual experiments, always for the STSB dataset, reporting on the Pearson correlation coefficient. If yes, does this affect the model's generalization capability? No, it does not. Another fun experiment that we did was we tried to adapt MD5 back to regression. So we explained already how it works, but what if we take STSB and we try to convert it back to a regression problem? So what we did is that we, of course, let the model make a prediction. It would output a string, and then we would convert it back to float. And then we would also convert all labels to floats. And then, of course, we would have to switch the loss function. We cannot use cross entropy anymore. So here we use a custom one, which is MEC plus some weight times the cross entropy. This one we empirically set to 0.1. We cannot see an improvement here, or we cannot see any significant improvement, which is a result in itself, because it says that MD5 works well already, at least for STSB. It doesn't need any modifications in the architecture whatsoever. So here we compare MD5 to a monolingual model, which is dedicated to Swedish, KBBERT, and the task is named entity recognition. We test the small and base version of the model, either on all entities that are present in the named entity recognition dataset that we use, which is SUC 3.0, or we only keep the three main entities in there, the most important classes. And then we compare against KBBERT, but KBBERT is way better for this particular task, named entity recognition. We do have to say here, though, that we had to pre-process the dataset, the named entity recognition examples in a specific way so that we could then feed them to MD5, and this might have compromised its performance. This is, again, a comparison between KBBERT and MD5, but this one is for SDSB. Here we find that MD5 is better, but we need to use the large version of it in order to beat KBBERT. And yes, in defense of KBBERT, I must also say that we did not fine tune it. We did not do hyperparameter tuning as extensively as we did for MD5. Yet it's really impressive how this model, which works the way it works, can reach a performance which is similar to an encoder-only model that is monolingual. So we move now to the second part of this presentation, which has to do with stereotypical biases. As a disclaimer, I would like to say that we studied only the binary case, she and he, but of course we are aware that it cannot depict the complexities of the biases with respect to gender bias, but we thought that it's still fine to obtain a coarse sense of those biases. And then it can be subject to future work to take into account all gender nuances. So we start from the background section again. So what is the motivation? Why did we include those experiments in this study? So we have our training dataset. We train our model on it, and then we do a downstream task. If there are stereotypical biases present encoded in the training dataset, then those are going to be manifested in the downstream task that we are going to be using the model on. So those can be harmful for specific groups, often marginalized groups, if we deploy and actually use those models in real life scenarios. So here we move on to the third question, which is, how can stereotypical biases be detected and measured in the model's contextualized representations, the embeddings? So we do some literature review here. Bias detection, it depends on the approach, how we do it, because it can be different for non-contextualized embeddings, fixed embeddings, and it has to be different for contextualized embeddings because those can change according to the sentence that they find themselves in. But those are fixed. So how we do it for non-contextualized embeddings, we are basically based on the seminal works of Polukbasi and Kaliskan. What we traditionally do, even the approaches that we use now are based on those two approaches, which is analogy tests and association tests. So analogy tests, what this is essentially is like we prompt the model, we ask the model if man is to a doctor, what this woman is to what, or maybe a more representative example is if king is to a man, then woman corresponds to what, and then the model is supposed to output queen, of course, and that would be normal. But here we see a biased case where man corresponds to doctor and woman corresponds to nurse. So we provide the model with A, B, and C, in this case, man, doctor, and woman, and then the output of the model, in this case, is nurse, which denotes gender bias with respect to occupation. And then we also use association tests. So here we have a good attribute and a bad attribute. So here we compute the distance between the word man and the bad attribute. We do the same for the good attribute and the same word. And then we subtract those two. And then we repeat for the word woman. And then those two subtractions, if the model is unbiased, should be equal. But this differs a lot when we try to do that, when we try to detect bias on contextualized embeddings. Those are some of the approaches that have been used lately. This is, we can comment on that now, or we can have it in the discussion later. But basically, it depends on the downstream tasks. There is no general solution fits all. So I'm just going to skip that for now, but we can also discuss it later. Part 2, stereotypical biases experiment section. So let's see what is our approach, how we try to measure and detect biases. So what we do first is we create a data set. Then we detect the bias on a downstream task on this data set. The downstream task is semantic text similarity again. And then we measure bias on contextualized embeddings. Moving on to how we create the dataset. So what we do is we get the test set of the SDSB. So here you can see the raw data frame. As you can see, we have pairs of sentences and the floating points, which are the similarity scores again. What we do then is we only keep the sentences that start from a man or a woman or he and she, and discard the sentences with pronouns because we don't want anything in the sentence that is disclosing information about the gender. And then we do counterfactual data augmentation. What we actually do here is when we have a sentence which is like, he is cutting up a cucumber, then we would substitute he with she. And this way we augment our data set. And then we do the same for an occupation. For example, we do that for nurse. We do not only do it for one occupation, rather we do it for 50 different occupations. And what we end up with is a final data frame of 150 rows and 52 columns, as that's the number of the occupations. So we have nurse, doctor, engineer, programmer, housekeeper, etc. So first, we detect bias on a downstream task, an ad hoc approach. So how do we do that? So for every occupation, we have a pair of sentences for the word man and another pair of sentences for the word woman. So here that would be a man is walking, a nurse is walking, a woman is working, a nurse is walking. Since we have 150 rows, that would be multiplied by 150. So this is why we would have a mean similarity score here, one for male and one for female. And we expect those similarity scores to be the same should the model be unbiased, which is not the case. So here what we see is, so we work with T5 model, and here we can see an experiment where we test the small base and large version of the same model for the occupation nurse, and we can see the difference between the similarity scores getting bigger. For example, here as male is the first bar, and then we have as female. And it's getting bigger and bigger as the model grows larger. We cannot see the bias emerging in the small version of the model, but we can see it emerging more and more as the model grows larger. That was for one. Occupation. Here we can see all 50 occupations. Previously it was T5, now it is MT5, which gives us the opportunity to compare between English and Swedish. So here you can see English and here you can see Swedish. So yes, an interesting observation here is that, as you can see, there is sometimes statistical significance hinders us from, prevents us from actually deriving a conclusion, but that's not always the case. So when we do have results that we can rely on, we can see that most of the times the differences in the Swedish language are smaller than they are in the English language. And here we can see the same thing again, but this time only for one occupation, and then comparison between small, base, and large for MT5 in English and in Swedish. And yes, this can be seen more clearly here. So yes, moving on to the other approach of measuring bias on contextualized embeddings. So what we do here is we start off again from the dataset that we have created. This consists of 150 rows. And what we do is we feed those sentences to MT5, and then we get the embeddings of the words that we get out of the last encoder. We have 150 sentences, so we end up having 150 he embeddings. Those are contextualized. So those are different. They are not the same every time, because he is in a different, the word he is in a different sentence every time. So we have 150 different he embeddings. The same for she, and the same for an occupation. So what we want to do is we want to find like a gender direction in T5's embedding space. So in order to do that, in order to see if we can do that, we take the Euclidean distance of he and she, and we see that we see the mean value and the STD. We get something like 2.0 plus minus 0.02. So we see a small STD compared to the mean value. And then what we do is we also take the angles between he and she. And that is what you can see here. You can see that they are not varying too much from the mean value. So based on that finding, we say that there might exist a stable gender direction in T5's embedding space, even though it is a mutable embedding space, because this is a transformer and the embeddings are not the same every time. So based on that, we go ahead and compute G, which is merely vector she minus he. Since we have 150 sentences, we do this 150 times and we get the average gender direction. What do we need it for? We need it to put it here. So this is our measure of gender polarity, which means whether an occupation, a word, is more associated to she or he. So this is nothing more like a projection of a word, a normalized projection of a word to the gender direction. The word here would be the word nurse. But since we have 150 nurse embeddings, we would end up having 150 BIs. And that corresponds to a distribution. So we thought we should just plot this and see if there is a signal. Maybe we get something like a normal distribution or something, and maybe we can get something out of it. And indeed we do. So here you can see the distribution of the 150 BIs for C. Here you can see the distribution of the 150 BIs for he. And then for the occupations, this one here is nurse, black is homemaker, yellow is teacher, and then this one here is receptionist, and then we have engineer, surgeon, programmer. This is the small version of the model, but if we use the large version of the model, then you can see the distribution of nurse, homemaker, and receptionist going towards the she distribution. And then you can see programmer, engineering being closer to the he distribution. So this is actually T5 saying that, hey, I think that nurse and receptionist is more correlated to she than it is to he. And a programmer might be more correlated as a word to he than it should be to she. And this is what this model is going to behave on, and to behave based on this when it performs like a downstream task. So conclusions. We followed a twofold approach. We first quantified gender bias on the embeddings using BI, gender polarity. We did the same, but using an approach based on a downstream task. And both approaches yielded the same results. Some of the occupations were more correlated to the word she rather than he. And those would be the same in both approaches. Then we found that the Swedish language might carry less biases with respect to gender stereotypes, which is a very interesting conclusion, given that when we pre-train a model on a language, it does not only learn the grammatical structure or whatever rule that is there linguistically, but it also picks up on information about what information is communicated in that pre-training text. And if less biases are present in there, then the model is going to be less biased in that particular language as well. And then, as we saw before, biases emerge for larger versions of D5, but they subside for the small version for specific occupations. And that might be merely because the model is not large enough to capture those biases, not because they are not there. Revisiting the research questions again. So we were trying to answer the third one. How can stereotypical biases be detected and measured in the model's contextualized representations? We used gender polarity for that, and we compared that to another approach that was using a downstream task. And that was the presentation. I am very happy to take any questions and have a discussion at this point.
Great. Thanks, Stella. That was an excellent presentation and a very interesting topic and very interesting result. We do have some questions in the chat. First off was Fredrik.